Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Today I would like to present about our research in the International Conference on Mechanical Engineering Research and Application ECOMERA 2020, and our title is Improved Mechanical Properties with the Soaking Time of NaOH in Composites Made from Sugarcane Bagasse Fibers for Future Windmill Blades Material. This is my name, Andromeda Laksono, and this is our members. This is my profile. So I'm a lecturer of Material and Metallurgical Engineering, Institute Teknologi Kalimantan, with topic of interest interfacial reactions, natural fiber composite, and innovative material. And this is the outline that I'm gonna talking about. I'm gonna introduce about my background in this research. The second is about the experimental method. The third, I'm gonna talk about my results, then summarize my work. The last one, there is a question and answer session, but maybe not in this session because this is asynchronous. This is about the introduction. Let's talk about synthetic fibers. Wind turbines come in several sizes. In small scale models used for providing electricity to rural homes or cabins, and community scale models used for providing community at industrial scales. Many large turbines are collected into wind farms located in rural areas or offshore. The term windmill, which typically refers to conversion of wind energy into power for milling or pumping. Materials for the wind turbine blade market include resins of glass fiber reinforced polyester, glass fiber, reinforced epoxy, and carbon fiber. However, there are weaknesses. It's about the availability and health factors, expensive costs, and also non-biodegradable. And this is the solution from us, natural fiber composites. The type of natural fiber composite, or NFC, has its own advantage compared to other alternative engineering materials, including strong, lightweight, corrosion resistant, low density, non-abrasive, biodegradability, abundant, and then also low cost. So talks about alkalization. So natural fiber composite needs the treatment called alkalization. NFC, such as sugarcane bagasse, is complex composite that composed of cellulose around 40 until 50%, and then hemicellulose around 25 until 35%, and also lignin 15 until 35%. And according to the reference Kumar et al. 2014, sugarcane bagasse composed this one, but we need to remove the three there are hemicellulose, lignin, and impurities. And we know that natural fiber reinforced polymers NFRP is several studies about combining NFC into polymer. So that's why we need alkaline treatment in AOH for the effect to make the composite more stronger, and this advantage can be increase the mechanical properties. So in this study, the focus of the study was to determine the effect of 5% AAOH alkalization on composite materials made from natural fibers. There is waste sugarcane bagasse fiber 40% and epoxy matrix 60%. And the alkalization time is about 1, 2, and 3 hours. And this is our characterization using tensile machine, impact machine, and then SEM. And the methods, we prepare the sugarcane fibers in Balikpapan. We cut and then we squeeze using press make pulp, And then also there is another preparations like cut into uniform lengths 10 centimeter, soak with ethanol to make it clean, drying, and then wigging. And this is the first test is moisture testing. So we need to make sure how many moisture in the sugar cane. And then in the variation in fiber treatment, we have 4 without treatment, and then alkalization 1 hour, 2 hours, and 3 hours. And then we treat in the box like in this picture, and then we drying in the oven. And this is about the preparation for testing. So we use HTM standard, and then we pour in the mold to make the impact test and tensile test. And this is the mold in volume, fiber in volume, and fiber mesh. And then the composite manufacturing, as I said before, is according to STM's D638 for the tensile, and the impact STM D61104. And also we use a mechanical test, and then also the characterization SEM to see to observe the fiber surface interface, and we analyze the fracture patterns. And here the results about the moisture test results. The data obtained are shown in table 2. The average moisture content obtained 7.69% in the standard, but in the actual the content is 11.99%. So this means it means the water content of sugarcane bagasse has decreased in water content that is greater than the standard water content results. Therefore, sugarcane bagasse used with the result of actual data drying can be applied in making composites. And about the impact test, we see the highest impact energy in soaking for 2 hours. We have 12 joule, and then in the impact strength graph also in soaking for 2 hours. So with the results of impact testing, this means their effect of the soaking for many times, but in 3 hours we have a decrease value for the impact. And about the tensile also modulus of elasticity, the 2 hours have the highest value in the tensile. It means the greatest possibility of decrease in strength in 3 hours in composite with variation in specimens without alkali treatment is because optimal distribution of stress received by the matrix to the fiber due to using the simple method of hand layup. So we use this experiments, use the simple one is hand layup. And this is the strain graph. So the decrease in strain value on composites with 5% NaOH for 2 hours is supported by the theory that plant fibers in general have higher stiffness and strength when gives an effect based on extraction method. In this case, the type of plant fibers was bagasse with the alkalization extraction method. And this is about the microscopic fractograph after impact and the tensile. So this is about the failure that occur were dominated by fiber pull out, which means the fiber absorbs more energy, so that the interface between the bagasse fiber and the epoxy matrix was stronger. And talk about the microscopic fractographs. We see there's a debonding fracture, and then also fiber pull out. This is SEM with 300 times magnification that we can see there are many defects in fiber pull out and debonding. So further research needs to be done in the form of fluorescence in fiber orientation, matrix selection, merging biaxial and triaxial directions, and advanced methods such as vacuum batching process, vacuum infusion process, and compression molding. So the conclusion in this research, so the value of the average stress absorbed impact energy obtained 12 joule, and the value of the impact strength about obtained 0.096. The value of tensile strength 9 MPa, and then the modulus of elasticity obtained 809 MPa, and then the characterization SEM show a failure in the form fiber pull out and debonding. Okay, thank you for your attention.